Hello, this is a video explaining the wave behavior you saw in your lab related to refraction. Just a reminder that refraction is what the wave does when it transitions from one material to another, and it's what the wave is doing in that new material. Before we actually talk about refraction, we need to review a little bit about impedance. Remember that impedance determines the speed and the wavelength of the wave in that material. And the impedance is determined by the property of the material. Is it high tension? Is it high mass? What's going on with that material? However, frequency is not determined by the material or the impedance. What determines frequency? Literally, how many shakes of the hand you've done to that material to put the waves in. So when a wave changes materials or impedance, it'll change its speed and wavelength, but that will never change the frequency of the wave. Because if the frequency of the wave would change here, then somehow you would have had to get rid of an oscillation or a pulse or energy that you put into that wave. And we know that can't happen by the law of conservation of energy. The best analogy I can give you for this is a highway analogy. I gave you this when we first were learning about impedance. I'm going to kind of expand upon it. So imagine that you've got a set of cars who are in a 65-mile-an-hour speed zone. They're able to go real fast. They have very low impedance, and the distance between the cars is pretty far. Then all of a sudden, those cars encounter this construction zone here in this picture. Uh-oh, now they're stuck down to 35 miles an hour. So they're not able to go as fast. They're more impeded in their motion, and there's going to be closer spacing between the cars. But what if you were to count the cars going from the 65-mile-an-hour zone to the 35-mile-an-hour construction zone? The count of the cars going from one zone to another would have to be the same. Of course, in this analogy, assuming that there is no exit ramps on the highway. That count is the frequency, because the frequency of a wave is literally the number of cycles per second. And so that is kind of another way of explaining why the frequency has to be the same. All right, so let's apply that to this example. What you see here on this slide is a visualization of waves as they go from one material to another, and which one is the higher impedance material. And I want you to compare the material's wavelength, frequency, and speed. Go ahead and pause the video and work that out. Okay, do you have your answer? If you said that the material on the right side of the screen is the higher impedance material, you are correct. It's going to be the higher impedance material because the waves have that shorter wavelength, they're bunched up, they're closer together, meaning that they're going at a slower speed. Both of them are going to have the same frequency for the reasons we've just talked about. In terms of the wave equation, that kind of makes sense. If you keep frequency constant, then if you have a shorter wavelength, then you are going to have a slower speed, because those two things are directly related. All right, let's actually apply this now to a wave situation. So we're going to first start off with a thin rope going into a thick rope. What you'll see I have on the screen here is what we talked about in a previous video, is what the reflected pulse looks like. That's the one that stays inside of that thin rope. What would it look like going into the thick rope? Here's actually the answer. The wave stays upright when it goes into the new material. And the reason for that is that when the wave encounters the boundary here, the wave coming in here is starting to lift up, and there really is no reason and no way for it to go down as it goes into this new material. If you kind of think about it, Newton's first law is going to make it go in the same way it was going originally. So it's going to cause an upward displacement. And so we're going to get a crest into the new material. This is a thicker material, of course, with a higher impedance, so that is going to have an implication on both the speed and the wavelength. It's going to be a slower speed and a shorter wavelength. In terms of the amplitude, I've drawn it with a smaller amplitude in this picture, but really, for our course, amplitude is unknown. The amplitude does correspond to the energy. We know it's going to give some of its energy over, but how that is going to translate into a new material is stuff that we're just not going to predict. The frequency will remain constant for the reasons that we've talked about on the previous slide. All right, what about if we go from a thick material to a thin material? Again, you'll see that I've put the reflected pulse that we've done from the previous example. And then what we're going to see here is going into a thin material. It is going to stay upright, and the wave itself will be much longer in its wavelength. So again, it's going to remain upright for the same reasons we talked about on the previous slide. There's just no force there, no reason for it to want to flip over at all. And so this new thin material is going to be lower impedance, so the wave is going to be going faster and therefore having a longer wavelength. Again, we're going to talk about how the amplitude is going to be unknown here. I've drawn it bigger. That may be a good guess. I don't know. It just depends how much energy it wants to transfer over and how easily that energy is translated into the amplitude of the wave beyond the scope of our course. And then, of course, again, frequency is going to remain constant. So in summary, when waves enter into a new material, the frequency of the wave remains constant. The wave that goes in, the refracted wave, is always going to be upright. So if you send a crest, you're going to get a crest in the new material. If you send a trough, you're going to get a trough in the new material. Wavelength and speed are going to depend on the impedance of that material. If you go into a high impedance material, you're going to get a slower speed and a shorter wavelength. Vice versa if you go into a lower impedance material. And for our purposes, the amplitude of the wave is going to be unknown beyond the scope of our course. So what you see here is a video of two slinkies that are attached together. And my question for you is, what is the impedance of the first slinky here, the silver slinky, compared to the second slinky, the darker, the black slinky? Let's watch the video. Do you have an answer? Let's watch the video again. Right there gives us some evidence. What I'm seeing is that I'm seeing the wave that is staying in the silver slinky is starting to flip over. But the wave that is into the darker slinky is staying upright. The fact that the wave flipped over gives us a sense that this silver slinky must be a lower impedance than the black slinky. So we're going to watch it one more time, this time looking at the wavelength. So I can see here get approximate wavelength on the silver slinky. Right here, I can get a sense of when it goes into the black slinky, that wavelength is definitely decreased, which tells us, again, that the black slinky has the lower impedance. All right, that is all for this lesson. Of course, if you have any questions, please let me know, and happy learning.